Colligative Properties Part 2, Freezing Point Depression and Osmosis. Freezing point depression is similar to boiling point elevation in the way that it mathematically works out. The freezing point of any substance is the point at which the particles move slow enough for the attractive force to overcome kinetic energy and cause them to condense from a liquid to a solid phase. At this point, the solid and liquid are in equilibrium with each other, such that solid particles are freely interconverting to liquid particles and back. In any sort of freezing process, the solvent will freeze before the solute will freeze because it's present in a much higher quantity. As the solvent begins to freeze, the solute is left out of the freezing process initially. So the number of solvent particles versus solute particles will change, where there will become more solute versus solvent than there was before the freezing began. So the overall concentration of the solution in terms of the solute will increase. The other solvent particles then are going to experience a higher degree of separation from each other because there are fewer solvent particles. The solution is being pushed into a smaller area, and the solute particles are making up more of the solution than they were before. So they're going to separate the solvent particles out more. As they do this, this makes the attractive forces have to reach over a longer range than they did before. Recall from Coulomb's law that the attractive force is proportional to the charges divided by the distance squared. So as the distance increases, the force decreases. This means that kinetic energy must decrease even further before those attractive forces are strong enough to pull the solvent into connection to each other and cause them to solidify. The decrease in a freezing point temperature is generally abbreviated T sub F. So the change in freezing point will be equal to the freezing point of the pure solvent minus the freezing point of the solution. We can mathematically express this as the change in freezing point being equal to a constant times the mole concentration of solute. The Kf is a proportionality constant which is analogous to the Kb for boiling point elevation and is called the mole freezing point depression constant. The change in freezing point by 1 mole ideal solution is what this constant represents, and it is measured in degrees Celsius per mole. M is the molality of the solute, and delta T sub F is the freezing point decrease that occurs. As an example, if we wanted to calculate the freezing point of a 1.7 mole ethylene glycol solution, if its normal freezing point is 0.0 degrees Celsius, and the Kf is 1.86 degrees Celsius per mole. Using the equation that we have, delta T sub F equals Kfm, we find that the change in freezing point is equal to the constant 1.86 degrees Celsius per mole times a mole concentration of 1.7 m equals a 3.2 degrees Celsius change. If the difference in freezing point is going to be equal to the freezing point of the pure solvent minus the freezing point of solution, then the temperature of the solution, freezing point of the solution is going to be equal to the freezing point of the pure solvent minus the change in temperature, rearranging the equation. So here, in order to find the freezing point of the solution, we will take the freezing point of the pure solvent and subtract out the change. In this case then, the freezing point of the solution is going to equal 0.0 degrees Celsius minus 3.2, or a minus 3.2 degrees Celsius freezing point for the solution. Osmosis is the fourth colligative property, which we will talk about, and is important particularly in things like biological activity, in order for cells to survive, because the passing of nutrients and things across cell membranes is important for their survival. And it's important for things like purification techniques. For instance, reverse osmosis, which is used if you ever go to the grocery store and buy bottled water, often you'll see that it's purified by reverse osmosis. Diffusion is a property that osmosis relies on. Diffusion is the movement of anything from a high concentration to a low concentration. If we look at this, for example, if all of the blue particles are concentrated on one side of the container by a wall that separates them, if we remove the wall, then over time they will spread out until they equilibrate throughout the container. As diffusion begins to occur, it causes a gradient, or a transition. So we see from the point at which diffusion starts, where everything is concentrated on one side, to the point at which diffusion ends, there's a graduation throughout that process where concentration changes continually. Eventually, it reaches an equilibrium point at which concentration is uniform throughout the container. Diffusion can be stopped by an impermeable membrane. This means that it's a membrane that can't be crossed. On the other hand, if I have a selectively permeable membrane, one that will allow some things through and others to be blocked, we can have controlled diffusion. This is what happens in the case of something like a cell membrane. It allows smaller particles like water through, but blocks large particles like proteins. In this example below, the red dots are able to pass through the barrier, but the blue dots are not able to pass through the barrier. So the membrane is selectively permeable and allows red dots through, but does not allow blue dots through. In a selectively permeable membrane, oftentimes it is the solute that is blocked by the membrane. In these cases, if solvent can cross, it will cross instead to try to equilibrate concentration. We want to equalize the concentration on both sides of the membrane because that's what diffusion does. And the process of a diffusion occurring across a selectively permeable membrane is referred to as osmosis. Initially, the rate of the osmosis will be proportional to the difference in concentration on either side of the membrane. As osmosis continues, solvent builds up on the side of the membrane to which the solvent is moving. Eventually, that solvent will exert a pressure on the membrane, which is called osmotic pressure. The pressure forces particles back across the membrane over time, and eventually the flow of particles back and forth across the membrane will reach a point at which there is an equilibrium in concentration on both sides. At this point, osmosis will stop. So we can refer to osmotic pressure then as being the exact pressure that is needed to prevent osmosis from occurring. Osmotic pressure in dilute solutions behaves very similarly to movement in an ideal gas. We consider in a dilute solution that solute particles don't interact with each other, the same way that an ideal gas does. And we abbreviate osmotic pressure using the symbol pi. So in this case, the osmotic pressure is equal to the number of moles times the gas constant R times temperature divided by volume. In molar terms, where molar refers to number of moles per liter, we have our osmotic pressure equal to the molar concentration times RT. As an example, the osmotic pressure of a solution containing 5.87 milligrams of an unknown protein per 10 milliliters of solution is 2.45 torr at 25 degrees Celsius. Find the molar mass of the unknown protein. We have our equation where osmotic pressure is equal to the molar concentration times RT. Solving for the molar concentration then, we first have to convert into the gas constant terms. 2.45 torr can be converted to atmospheres by multiplying by 1 atmosphere per 760 torr, and we get a result of 0.003223 atmospheres. 25 degrees Celsius, likewise, by adding 273 gives us 298 Kelvin as the temperature. We can rearrange to solve for molar by dividing the osmotic pressure by RT, isolating molar on one side. The molar concentration then is equal to the osmotic pressure of 0.003223 atmospheres divided by the combination of the gas constant 0.0821 liter atmospheres per mole Kelvin times the 298 Kelvin temperature. This will give us a molarity of 1.318 times 10 to the minus 4 molar. If we take our 10 milliliters of solution and convert them to liters by multiplying by 1 liter per 1,000 milliliters, and then multiply liters by molar, we'll get moles, because molar being moles per liter, if multiplied by liters, cancels out to form moles. If I multiply this across, I would get a 1.318 times 10 to the minus 6 number of moles. If we take our mass, 5.87 milligrams, convert it to grams by dividing by 1,000 milligrams per gram, we will get the number of grams. If we take grams and divide that by moles, we'll get the gram per mole molar mass. So 5.87 milligrams converted to grams and then divided by 1.318 times 10 to the minus 6 moles gives us an overall molar mass of 4.45 times 10 to the third grams per mole. Now osmosis varies depending upon a number of things. Temperature is very important to osmosis because pressure is temperature dependent. In addition, the effect of the osmosis itself depends on the nature of the solutions inside and outside of the membrane. If I have a high concentration, that will be the same as having a high solute versus solvent ratio. So as solvent begins to move across, the ratio of solute to solvent decreases, which lowers the concentration. If I have high concentration of solute outside the membrane versus inside, this is referred to as hypertonic, where hyper means more than. High concentration of solute inside the membrane versus outside the membrane is called hypotonic, where hypo is less than. If there are equal concentrations of solute both inside and out, this is called isotonic, because iso is equal to. In a hypertonic solution, we will tend to dilute the outside as solvent moves out of the membrane. In a hypotonic solution, we'll dilute the inside as solvent moves in. In an isotonic solution, there will be no net change in solvent because the concentrations are equal. So as a visual example of a hypertonic solution, we see that there are many more blue particles outside of the membrane than there are inside. This means that the overall concentration outside is higher than inside, and the movement of osmosis will attempt to dilute the outside of the membrane. This causes solvent to move out of the membrane and decreases the osmotic pressure inside the membrane, causing the membrane to shrink. The next example is a hypotonic solution, where there are many more particles inside than outside. This means that the outside is going to want to dilute the inside, causing solvent to move in. As solvent moves in, the osmotic pressure increases, and the membrane will expand. In the last example, there's an even number of particles inside and outside. In this instance, the concentrations are equal, and there is no net change in the solvent, so there is neither a greater movement in nor out of the membrane.